Today we're diving into one of the most astonishing breakthroughs in AI-driven graphics we've seen yet. Microsoft has developed an artificial intelligence system that can ray trace, wait for it, 16 million images in parallel. That's not a typo, 16 million. This could completely change how we render graphics in games, simulations, and virtual worlds. Let's break it down. What is ray tracing? Before we jump into Microsoft's AI, let's take a moment to understand why ray tracing matters so much. Ray tracing is a graphics technique that simulates how light bounces around the environment. It traces rays of light from your eyes, or the camera, through a 3D scene, bouncing off surfaces, casting shadows, creating reflections and refractions, just like light behaves in the real world. This creates incredibly realistic lighting, but it's also incredibly computationally expensive. Even with the most powerful gaming GPUs, ray tracing is still limited. You often need to lower resolution, frame rates, or compromise elsewhere. So what did Microsoft do? Here's where Microsoft's new AI comes in. They've created a system that uses deep learning to essentially learn how ray tracing works across a massive range of visual scenes, and then generate photorealistic ray-traced images in parallel. How many images? 16 million. At once. Let that sink in. This isn't traditional rendering. It's not running on a single graphics card trying to trace millions of rays in real time. Instead, Microsoft's AI is doing something smarter. It's learning patterns. How does it work? At a high level, the AI is trained on an enormous data set of real and simulated images that already have ray-traced lighting baked in. These images teach the AI what realistic lighting looks like, what happens when sunlight bounces off a marble floor, or when fog interacts with neon signs at night. The model learns to generalize this, so that when you feed it new, unseen images, it can predict what a fully ray-traced version would look like. And here's the mind-blowing part. The system can infer these outputs across 16 million images at once, thanks to its highly parallel architecture. In practice, that means this AI can take raw or low-quality renders from, say, a game engine, and output millions of high-fidelity, ray-traced versions all at once. This has massive implications. Implication 1. Accelerating game development. One of the slowest parts of creating a game is the lighting and environment rendering. Artists have to bake lighting maps, test scenes under different conditions, render previews that take hours. This AI could cut that work down drastically. Imagine previewing your entire open world with ray-traced lighting instantly, or running lighting simulations for different times of day in seconds, not hours. Studios could iterate faster, experiment more, and still get cinema-quality lighting. Implication 2. Enhancing real-time graphics. While current GPUs like NVIDIA's RTX line support ray tracing, performance is still an issue. Even high-end systems struggle to push high rays, real-time ray tracing without sacrificing frame rate. But with AI-assisted rendering, you don't have to compute every light bounce. Instead, the AI can fill in the missing lighting details, enhancing the realism without crushing your GPU. This could open the door to mainstream games having RTX-level visuals without needing $2,000 hardware. Mobile gaming, VR, and cloud streaming all benefit. Implication 3. Simulation and beyond. Now let's go even further. Microsoft's system isn't just for games. It can be used for simulations. Weather systems, urban planning, autonomous vehicle training. Think about this. Self-driving cars rely on photorealistic simulated environments to train their AIs. With this system, you could generate millions of realistic training scenes, each lit differently with different times of day, fog, shadows, and glare, all crucial for robust training. Architects could preview entire buildings under realistic lighting in seconds. Scientists could visualize data under accurate environmental conditions. Future possibilities. It's hard not to imagine where this goes next. We're already seeing early steps toward a photorealistic metaverse, persistent digital worlds that feel nearly real. This technology could become a key piece of that puzzle. If you can render realistic lighting on a planetary scale across millions of environments simultaneously, we could soon have digital worlds that behave like physical ones, where light obeys the laws of physics, where every surface behaves naturally. It also blurs the line between simulation and reality, and that's both exciting and something we should approach thoughtfully. Ethical note. As always, powerful AI opens powerful questions. Who controls these tools? Will developers use them responsibly? Will realistic rendering be used in deceptive media or deepfakes? These are ongoing challenges. But as researchers and creators, the more we understand the tech, the better prepared we are to use it well.